Today we will be solving some questions, some selected questions from Unit 2, May 2025. Let us move on to question number 1. It says, what is the expression for the enthalpy change of neutralization of sodium hydroxide in joules per mole? It says expression for the enthalpy change of the neutralization of sodium hydroxide and ethanoic acid. And enthalpy change or neutralization is the energy change when 1 mole of water is formed, right? It is the energy change when 1 mole of water is formed, when an acid is neutralized by excess base, or when a base is neutralized by excess acid. Now, firstly, what we need to do is we need to find the energy change during the reaction. Energy change during the reaction equals m into c into delta T. Now, the mass of the solution would be 25 plus 30, because it says 25 cm³ sodium hydroxide solution was added to 30 cm³ ethanoic acid. So 25 was added to 30. So the total volume here comes out to be 55 multiplied by 4.18. 4.18 is the specific capacity of the mixture multiplied by the temperature change. Now the temperature change here was found to be 6.5. 6.5 is the temperature change, right? So multiplied by 6.5. So that would be the energy change in joules. Okay. Then you need to find the moles of water formed during the reaction. Now the moles of water formed can be found from the moles of either the acid or the base. But firstly, you need to figure out which one of them was the limiting reagent, because the moles of water formed will depend on the moles of the limiting reagent and not on the excess. So firstly, what we should do is we should find the moles of the acid and the moles of the base. Firstly, we should find the moles of the base. Moles of sodium hydroxide is 2 multiplied by 25 into 10 to the power minus 3. If you calculate this, this is found to be 2 into 25 divided by 1000 will give you 0.05. Then you also calculate the moles of ethanoic acid. Moles of ethanoic acid has a concentration of 1 and a volume of 30. So you multiply 1 multiplied by 30 into 10 to the power minus 3. So 30 divided by 1000 will give you 0.03, right? So sodium hydroxide is in excess, and ethanoic acid is the one which is the limiting reagent. So the moles of water formed will be equal to the moles of ethanoic acid that reacted, moles of CH3COH. So this would be equals to 0.03. So then you find del H. Del H will be the energy change. The energy change is 55 into 4.18 into 6.5. You divide this. So you divide this by the number of moles of water formed, which is 0.003. And you put a negative sign because there was a temperature rise during the reaction, indicating an exothermic reaction. All right. Then we move on to question number 2. It says a data book value for the standard enthalpy change of combustion of methane is minus 890. Okay. What is the experimental value for the enthalpy change of vaporization in water in kilojoules per mole? Okay. See, when water is in the gaseous state, the del H is minus 810, right? When water is in the gaseous state. Now, the standard value, if you look at the standard value, sorry. Now, when you look at the standard value for the enthalpy change of combustion of methane is minus 890. right? Now there is a difference. If you look here, there is a difference. When water is formed in the gaseous state, the delH is minus 810. When water is formed in the liquid state, because when you are dealing with standard enthalpy change of combustion, water is considered to be in the liquid state, right? So when water is formed in the liquid state, the enthalpy change is minus 890. When water is formed in the gaseous state, the energy change is 810, right? So what they asked, that what is the experimental value for the enthalpy change of vaporization of water? H2O liquid turning into H2O gas. See, H2O liquid turns into H2O gas, right? H2O liquid is turning into H2O gas. So this will be endothermic, right? Since it's a liquid turning into gas, the conversion should be endothermic, and that is why we will be ruling out options A and C will be ruled out. Because when you turn liquid to gas, the process is endothermic, right? This process is endothermic. So what we do here basically, we'll find the difference between 810 and 890. Now the difference between 890 and 810 is 80 kilojoules, but 80 kilojoule is not the answer. Because these energy changes, 890 and 810, were for 2 moles of water formed. The energy changes, 890 and 810, were for 2 moles of water formed. See, in the question, in the balanced equation, water formed is 2 moles, right? The moles of water formed are 2 moles of water. But they asked the enthalpy change for the vaporization of water, where water is only 1 mole. For 2 moles of water formed, the change is 80. So for 1 mole of water formed will be 80 divided by 2, which is 40. Get the point? You find the difference, and the difference is for the enthalpy change of vaporization of 2 moles of water, not for 1 mole of water. So they asked for the enthalpy change of vaporization for 1 mole of water. So for 2 moles of water, it's 80. So for 1 mole of water, it would be divided by 2. So with this, that would be equal to 40. So the answer must be B. Alright. Then we move on to the next question. Question number 7. It says, which electron movement causes the yellow color produced in a sodium chloride in a flame test? Now, in any flame test, the color is caused because electrons are excited and electrons move to the higher energy orbitals. And when they drop back from the higher energy orbitals to the lower energy orbitals, they release some radiation. They emit some photon or they emit radiation. That is why you see a color, because the frequency of the radiation is within the visible range, and that is when you see a color. So it says addition of an electron to a sodium ion. Wrong statement, completely wrong. Ruling out this statement. If you add an electron to a sodium ion, so that is something that doesn't happen during a flame test. During a flame test, electrons are excited to a higher energy orbital or higher energy state, and they drop down to the lower energy state, and then they release some radiation. It says an electron moving from a 3s to a 3p orbital. No, you don't see a color because electron moving from a lower to higher energy orbital. You see a color when electrons move from higher energy orbital to a lower energy orbital. So that is also wrong. So we are ruling out option number C. Removal of an electron from a sodium atom. Removal of an electron from a sodium atom is ionization. We are not ionizing here. In a flame test, electrons are not removed from a sodium atom during a flame test. So that is also wrong. So B is definitely the answer. An electron moving from a 3p orbital to a 3s orbital, because the color is seen whenever electrons move from higher energy orbitals to a lower energy orbital. 3p is a higher energy orbital, 3s is a lower energy orbital. So moving from 3p to 3s, electrons moving from 3p to 3s can actually show a color, because that would emit some radiation, and if the frequency of the radiation is within the visible range, then you would always see a color. Question number 8. It says 20 grams of an impure sample of calcium carbonate is heated and decomposes completely. 3.6 dm³ of carbon dioxide is produced at room temperature and pressure. What is the percentage purity of the sample? Okay. So 20 gram is the mass of the impure sample. Let us write the equation first. So calcium carbonate is being heated, it produces calcium oxide. It produces calcium oxide and produces carbon dioxide gas. So both of these are solids. 20 gram is impure. It produces 3.6 cubic decimeters of carbon dioxide. So what you initially do is you find the moles of carbon dioxide formed. Moles of carbon dioxide formed is 3.6 divided by 24. 24 is the molar volume of the gas. So 3.6 divided by 24 gives you 0.15. From the moles of carbon dioxide, you find the moles of calcium carbonate. The mole ratio is 1:1 according to the balanced equation, so this will also be 0.15. Then you calculate the mass of calcium carbonate. Mass of calcium carbonate will be 0.15 multiplied by the molar mass, which is 100. So if you multiply, this becomes 15 grams. So 15 gram is the mass of calcium carbonate that is involved here. Then you calculate the percentage purity of the sample. Percentage purity of the sample will be equals to mass of the calcium carbonate divided by the mass of the impure sample multiplied by 100. So 15 divided by 20 multiplied by 100 equals 75%. So your answer to this question would be D. Then we move on to question number 9. Question number 9, it says, in an experiment to measure the rate of the reaction, a sample of magnesium ribbon was 0.24 was added to 25 cm cube of sulfuric acid of concentration 1 mole per dm cube. Okay, you are given the mass, you are given the volume of the acid and the concentration of the acid. In a second experiment, they used powdered substance of the same mass and was added to 50 cm cube, right? Okay, and sulfuric acid had the same concentration. So what are the expected differences? Definitely if you use powder instead of the ribbon, the rate would be faster, right? The rate would be faster, so we choose option C and option D. The rate would clearly be faster because you have used powder instead of ribbon. So powder have greater surface area compared to the ribbon, right? The total volume of hydrogen gas produced. Now what about the total volume of hydrogen gas produced, right? Now the total volume of hydrogen gas produced won't change because magnesium was the limiting reagent here and sulfuric acid was in excess. So if you calculate, sulfuric acid has greater moles here compared to magnesium. So when sulfuric acid was 25 cm cube, it was in excess. When sulfuric acid was 50 cm cube, it was still in excess. So the volume of hydrogen gas produced will not change. For this, you can calculate the number of moles of magnesium and the number of moles of sulfuric acid. So if you calculate the moles of magnesium, it is 0.24 divided by 24.3. So 0.24 divided by 24.3 would be 0.00988. Right, this is the moles of magnesium. Then if you calculate the moles of sulfuric acid will be equals to 1 multiplied by 25 divided by 1000 will give you 0.025, right? So definitely sulfuric acid was already in excess. So sulfuric acid was already present in excess, right? So if you take even more sulfuric acid, the volume of hydrogen gas produced will not increase. It would remain the same. Okay. Then we move on to question number 10. Which change increases the proportion of particles in a reaction that have sufficient energy to react? Okay. Proportion of particles in a reaction that have sufficient energy. Of course, an increase in reaction temperature. if you increase the temperature, the proportion of the particles in a reaction that is sufficient energy to react increases. If you remember the Maxwell-Boltzmann distribution, we studied this in the Maxwell-Boltzmann distribution. In the distribution, if you increase the temperature, the curve changes, the peak decreases and peak shifts to the right. So the proportion of particles right to the activation energy increases, right, which have energy greater than the activation energy. So when you increase the temperature, the area under the curve right to the EA line increases. So more proportion of molecules have energy greater than the activation energy, right? Alright, then we move on to question number 13.